Okay, we are recording, hopefully.
All right. So, hi, everyone. Thanks for coming to our presentation on what goes into making QuaCS, self-imposed problems for fun and profit. We're just going to be talking a little bit about QuaCS, the background of QuaCS, what goes into making it, stuff like that. Next slide. If you're interested in the presentation, the source is linked there, but you can view the actual slides in the workshops channel. It's all open source, the presentation, so feel free to take a look.
I
Next
sent it in
slide.
the slides channel, not the workshops channel.
My bad.
All right.
So what is QuaCS? Oh, sorry. My bad. You can go.
Yeah. So
But this
before
is my
we,
slide. It says Eli in the notes.
you,
I'm talking.
okay.
What is QuaCS? QuaCS is a course scheduling tool to help students pick which courses to register. So with QuaCS, you can look at the website, and it allows you to see all the courses that RPI has at the current moment for any semester, going back a number of semesters. And you're able to look at them, pick different courses you want to take. It helps you deal with a bunch of different things like conflicts, stuff like that.
Next. Yes.
Yeah.
All right. So some of the key features of QuaCS are automatic schedule generation. So as you select courses and sections, it will automatically generate all possible schedules which can be made from those courses and sections. It'll also, while you're going through the process of picking sections, it will determine which courses can still be taken, whether or not there's a time conflict, for example. We also can check if you meet the prerequisites for a given course. You can either manually enter which courses you've taken, or if you upload a copy of your transcript, then it will be able to figure it out from there. The data is always up to date within an hour or two. And you can always view past semesters. We have all the scheduling info going back to fall 2007. So some of our goals, as I said, always up-to-date data. This is one of the most important features of a course scheduler. If what you see on the website is not what is going to be used when you actually register, then there really isn't a point in using the site. We want to have zero maintenance. Neither of us are interested in maintaining a server, and we want QuaCS to be able to survive after we graduate. So ideally, this site will be able to exist completely hands-off. Mobile-first design. If you're on a phone, you should have just as easy of an experience as if you are on a computer. Open data availability. All of our data that is used to power QuaCS is open source in a Git repo. Anyone is able to access it and do whatever they want with it. And above all else, the site needs to be fast. There's a lot of computation which goes into figuring out what these courses are and what the schedules can be. But at the end of the day, the user doesn't care about that. They just care about having as fast of a presentation, as fast of a website as possible. So in terms of our analytics and statistics, our analytics are publicly available at the link in the slides. Since we started tracking them in November 2020, we've had around 380 page views and 19.2 total visitors, or 19.2 thousand. It's worth noting that this doesn't account for Arch registration, which occurred a few days ago. But our best day was on November 9th, 2020, which was around when spring course registration was occurring. And to get an idea of what our analytics site looks like, here it is. If we look at the last 7 days, you can easily see when Arch registration happened. It was right here. And all this data is public to anyone who goes to share.quacs.stats.quacs.org. and anyone's able to look at all this info. It's all anonymized, so you're not going to be able to see, oh, Joe Johnson has signed up for a certain course. But it gives you an idea of how people are using the site.
So now I'm going to talk a little bit about the brief history of QuaCS. The initial plan for QuaCS was actually an April Fool's joke for our Rubber Duck Discord bot, which was an Arcos project in the past. And the idea was to make a course scheduler through Discord where you would use a bot. But then in March 2020, I was looking to sign up for our Arch registration last year. And QuaCS had not updated for Arch. There was no course scheduler. The only option was to use SYS. And so I looked at the problem, and I realized that it shouldn't be too hard to do. If I can scrape the data together, I can write a basic website, and I can get some basic conflict checking just to see that courses are not happening at the same time, which would be very helpful just for my personal Arch registration. And then I decided to post it online and see if anyone else wanted. So that's when old QuaCS was made. But then over Arch in June, Ben was at an internship, and I was working on my classes and my own separate Arcos project. But in our free time, we decided that we wanted to actually make QuaCS into something that was more useful than just the basic old QuaCS that barely worked, but sort of worked. So that's when we decided to make modern QuaCS. So we took some of our time, and we developed most of modern QuaCS in June of last summer. Then just a few other notable points. In October, we added previous semester support. So now you can look back at semesters all the way back to about 2007 and see which courses were added, which can be very helpful when trying to look at future courses or just fun to look at. And then officially in January 2020, this semester, we decided to join Arcos. And so now QuaCS is officially an Arcos project. And then coming full circle, in February, we released Arch support. So now the modern QuaCS has nice features to deal with 6-week courses, stuff like that for Arch. So we've come full circle since the original plan of the old QuaCS. Next.
Okay. So
wait, you skipped the web
I?
implementation. Yeah. You press next, not space.
All right. I guess I don't like
So
this.
now I'm just going to talk a little bit about how we implemented the website. Next. So QuaCS relies on a few different tools. The main thing we use is Vue.js. So that's a front-end framework. It's pretty modern, and it allows us to do all sorts of dynamic rendering, stuff like that when you're using the website, when you toggle different courses, all sorts of different features. Another cool thing about QuaCS is that it's a progressive web app, which is really nice because it allows us to take advantage of things like caching, but also the ability for you to install it on your device, and even it works fully offline. So if you load up QuaCS and then say you don't have internet but you want to check it out, you can load up QuaCS again, and it should totally work. The data will be obviously a little out of date, but it'll still work, and it's fully installable on your device. Next. Just a little bit more about our analytics. So we use this program called umami.is, which is a completely open source, privacy focused analytics tool. It's self-hosted. And as you saw before, it tracks the unique sessions, page views, events, stuff like that. And the main point that we use this is it helps us design or drive design choices. So as an example of that, we had this feature where you could go to the schedule and you could click on a CRN and it would copy it to your clipboard. But we noticed that people didn't really notice that, but they weren't really using it because we noticed that not a lot of people were doing it from our analytics. And we've been using that to help design and improve that and make it so that it's more obvious to users that stuff like that exists. So the analytics is extremely helpful with development. Next.
Okay, I think my spacebar just triggers twice. Okay, so one of the core features of QuaCS, as we mentioned, is that it can automatically determine whether or not two courses conflict with each other. So the problem in general terms is if I give you some courses and sections which have been selected, can you tell me which courses can still be registered for without any conflicts? And this sounds simple, but it gets a little more complicated when the user might have selected multiple sections from each of their courses. Now you need to try each one of those combinations. So let's try an example. So in this graphic, if two sections are vertically aligned, that means that they occur at the same time. So for example, section 2 of course B occurs at the same time as section 1 of course C. So given these sections, I've already signed up for this listed sections of course A and B, can I select those sections of course C? And the answer is yes, because we are able to make schedules out of these sections. Here's one possible schedule, here's another possible schedule, and here is a third possible schedule. So now I'm going through my course registration and I want to know, can I sign up for course D now that I've added A, B, and C? And can we add this? The answer is no, because if you remember from before, every single schedule that we generated has something in that time slot which the course D section occurs in. So now that you have an idea of this problem, you can start to imagine that it gets really difficult.
So what would be an algorithm we could use to try to solve this problem? Well, it seems like it would be a depth-first search, because it looks like a tree. So if you imagine each level is a course in the tree, or each level of the tree is a course. And then from each course, we have branches that represent each individual section. So a course might have 3 branches, it might have 20 branches, might just have 1 branch. And then for each of those branches, we have to check it against each of the other courses and branches, and we have to check that for every single time block. So if a course meets Monday, Thursday, and it has a Wednesday lab, you need to make sure that the Monday time blocks don't interfere with each other, the Wednesday lab doesn't interfere, and the Thursday time block. So you can imagine that the tree grows pretty big pretty quickly. And then the question is, given the tree, if we want to insert a new course, or a new section really, will it conflict? Will there be a problem? And with at least one of the schedules. Next. And so you can imagine this will take a while. Imagine a freshman taking CS1, Calc 1, and Chem 1, and then they want to add, say, a Haas course afterwards. CS1 has like 20 sections, Calc 1 has like 20 sections, and Chem 1 has like 20 sections. That's going to be a massive tree, and the thing is, the student only cares that at least one combination of CS1, Calc 1, and Chem 1 works. More is obviously fine, but there needs to be at least one combination. Next. So then the question is, can we mitigate the runtime here? So this is large. We don't want to take this to take very long. We don't want them sitting there for a minute every time they want to check if there's conflicts. So now we're just going to go into a few different ideas of how we might improve that. So the first one is, well, can we use our RPI education to improve the algorithm such that it's not just maybe a basic depth-first search, but something more complex? And despite Professor Brinsger's proof of P equals NP, we're unable to show that in practice. We have been unable to find a better solution to this problem than the basic depth-first search, as far as an algorithm is concerned. If you have any better solution and you can think of one, please let us know. We'd love to hear from you. Next. So that doesn't work. The next option is, well, maybe we only check a few schedules. Sure, we have 20 sections of each of those 3 courses, but the truth is, if it doesn't work in, say, the first N schedules, the first 1,000 schedules, is it really going to happen? You probably will just have a conflict by that point. So why do we have to check all these schedules? And that works for some people. It could work, but we don't think that's good enough for QuaCS. That's not something we want to implement, even if others are doing it that way. Next. All right, so another optimization we've tried is, well, if you remember, each section has all these time blocks that they have to deal with. And the question is, do we really need to compare each time block, Monday, Wednesday, Thursday, to each other time block of every other section? What if instead we pre-computed and we say each section keeps a list of all the sections it conflicts with? So your section 1 of data structures will keep a list of every single section at RPI it conflicts with, and then you can just cut off a lot of branches of that tree where you don't have to check the individual time blocks. And this works. This is a great solution. This speeds up the program a lot, but it does have a trade-off. It uses a lot more memory. And so, yes, you can compress it, you can try to store it, but at the end of the day, you're still storing a lot more information than just the basic times, because each section has to store a list of hundreds of other sections it conflicts with. But this does work. Next.
So now the next idea. As we all know, every program written in Rust instantly becomes way faster. So obviously, if we write our conflict checker in Rust, our conflict checker, just because it's written in Rust, it's blessed by the crab, it is much, much faster. And then, as a last case resort, assuming that these two green ticks don't work, we can always just upgrade our server, because we can just get a bit higher performance and then...
Wait. I thought we said we didn't want any maintenance. Why do we have to have a server? That's a lot of work. You got to maintain it. You have to pay for it. I don't really want a server.
Well, okay. Well, I guess we don't need a server. At the end of the day, I already know which courses I want to register for. I personally don't need to use QuaCS. So why don't I just go and offload all the information to the poor people who actually need to use QuaCS, and we can just run it on their computer. So now here's the new question. Given all of these constraints before, can we run this all in the browser?
So let's revisit some of the previous ideas we had. So the first was pre-compute the sections with each other. And so as I was saying, this totally works, it's valid, but the problem is it increases the memory. And there's really two ways to do this. You can pre-compute it on the page, or you can download it from the server. But both of those take a while to do. Downloading from the server, you're going to be downloading a massive file with all of these conflicts pre-computed. And so that's not really ideal, as well as if you want to store it in memory, it takes up a lot of memory on the front-end client, which is also not ideal. The other thing is writing in Rust, but there's a problem with that. Websites are written in JavaScript. You can't really write it in Rust if the website is written in JavaScript, and JavaScript is the language of the web. So that also doesn't work.
Wait, but I really like Rust. Is it possible to use Rust? It is. In case you have not heard of WebAssembly, WebAssembly is a semi-new standard for the web. It's essentially just assembly for the browser, as the name suggests. It's supposed to be an analog to running just compiled machine code on your own computer. The benefit of this is if you have a high-level language such as Rust or C++ that already has a very efficient optimizing compiler, and you are able to target that language to WebAssembly, now you can have all of those optimizations running inside the browser. You get all the benefits of those languages, such as type checking and borrow checking in Rust's case. And then you can bundle up that WebAssembly and ship it along with your browser, and your browser will just run it as if it was any other code which was shipped along with the site. So now that we know that we're writing this for the user's browser, we have some new ideas for how we can really eke out every last bit of performance. And all of these ideas are actually what are used on the QuaCS front end. So the first idea is to store times that a section occurs in a bit vector, which, if you're not familiar with the term, it's essentially like an arbitrary length integer, because integers are stored in binary where bits are 1 and 0. A bit vector just extends that to be any length you want. So we're going to say that every section has a bit vector that's the same length, and it's going to be 1 bit for every hour of the week. And a bit is going to be 1 for a given section when that section occurs, and a 0 for all the other times. So now each section has its own bit vector. In this example, if we have a section which is meeting at times T1 and T4 throughout the week, the T1 bit would be a 1, T2 and 3 would be a 0, T4 would be a 1, and T5 is a 0. And these, implementation-wise, can just be stored as a normal number. And some of the benefits of this is now we can check if a course conflicts with just a bitwise AND operation. If any 2 bits overlap between 2 sections, we know that those sections occur at the same time. This gives us the benefit of the um, uh, solution from beforehand where we were pre-computing which sections conflict with each other, but it has the upside of we don't now need to store all of those relations. We can do the same operation in the same amount of time with just one number stored per course. And then you can also, once you have all of these bit vectors, you can run an algorithm to determine that some bits aren't actually necessary for determining if two courses conflict. We're not going to go into how that works here, but if you are interested, reach out and we can discuss it. So now that we have all of these different bit vectors, we can store the entire time that a schedule occurs in by just ORing those bit vectors together. So now we have a single integer where a bit is 1 if you are taking a class at that time, and it is 0 if you are not. So now that bitwise AND from before, where we are checking if two sections conflict, now we can check if a section conflicts with the entire existing schedule, all in a single operation. And then the last thing which we do is we run this whole algorithm in a separate thread. That means that if for some reason it takes a really long time to run, your site is not going to freeze because you have selected 10,000 different sections of a course. It might not update which courses conflict right away, but you'll still be able to interact with the website, and the frame rate will remain high. So, does this work? We have all of our fancy optimizations, but if it didn't actually make the speed increase, it's useless. And if you have used QuaCS, you know that it does work. As the benchmark from before with CS1, Calc1, and Chem1, it took 2.45 milliseconds to generate all of those schedules. And then it takes some time to update the site. But the actual core algorithm is just this amount of time. And this is running in your browser. It will run extremely fast, both on a desktop, on a phone. You can run it on a really low-end computer, and it will still run very fast.
So now we're going to switch gears a little bit, and we're going to talk about the data collection and site generation. Next. So as you can imagine, QuaCS has a lot of data. We're storing stuff like the courses, we're storing the catalog. So how do we get all that? Well, the first place we look is we want to get the courses from SIS. SIS is the absolute truth when it comes to course registration. If it says it's available in SIS, it's available. If it says how many people are in it, that's what's like SIS is the truth. So we try to get our data directly from SIS to make it the most accurate and up to date. And the whole point is, the hope is that QuaCS looks almost exactly like SIS within an hour of the time, because we get the data about once every hour. Next. There are some other places we get data from. So we also get data, so we get the SIS data, right? That's the seats, the times, the prerequisites from SIS. But we also have to get the course descriptions from the course catalog, as well as we collect a ton of other data. One of the secret goals of QuaCS is that we just like to collect the data and put it in an open place for people to get. So some of the other data we have a massive JSON file of all the courses you can transfer into RPI, nicely formatted. So if you're wondering, hey, what course can I transfer in to get out of data structures, we have a massive file that has all of that information. Other stuff, we have a list of all the faculty member at RPI scraped from the faculty catalog. And actually, a sort of fun fact, well, maybe not so fun, but when RPI laid off a number of professors earlier this year due to COVID, they didn't really tell us who those professors were, but we were watching as the data changed on QuaCS in the GitHub repo of the data, and we were seeing as professors were moved from the faculty catalog, which is, it's good to have that data because you might be interested. And all of this is stored in our QuaCS data repo. So if you clone the repo, you get the most up-to-date data, but you can also look back at the Git history, and you can see as things change over time, which is really nice. Next.
All right. So now that we have gone through how we collect our data and what actually goes into the QuaCS website, these are the 5 steps which are needed to actually build the site. So step one is to scrape the data. We have our helper scripts to pull everything in. Step two, we need to build that WASM component. This is the course conflict checking and schedule generator, which is written in Rust. Step three, there's a little script which is used to hook into our analytics platform. And then step four, you put all those pieces together. You run yarn build. It builds the whole site all nice. And then step five, you go to whichever hosting service you prefer, upload the files, and QuaCS is there, ready to go. So for us, the way that we perform those steps is through GitHub Actions, which, if you're not familiar, are essentially just scripts which you can run on GitHub servers. If you're an open source project, they are free, and they are very nice. QuaCS is 100% run through GitHub Actions. So we have some standard actions. We have scripts that lint the code. It checks that there isn't a performance degradation, and then it checks for code quality and bugs. And these are all standard things that most sites have. We also have some QuaCS-specific actions. These are the ones for actually downloading the scripts. They're scheduled to run every hour, and there are 4 different actions, 1 per data source, give or take. We have an action which builds these site itself. If you're familiar with Vue and you've ever looked at the URL scheme which QuaCS uses, you might be confused by the fact that the pound sign indicator comes after the semester instead of before the semester. That is because every semester of QuaCS is a separate instance of the site. It's built separately, it's hosted in a different folder, and there is no interaction between the different sites. So we have one script which builds all of these semesters all together, just one after another, and then pushes to GitHub Pages, which is where we have our site hosted. The total time to scrape and deploy is about a bit under 40 minutes. And because we are hosted on GitHub Pages, we don't have to worry about a server, and we have 0 downtime.
Any questions? That's our presentation. Just something to note, if you're interested in our GitHub for our project, or if you're interested in joining our Discord server where we talk about QuaCS, all that stuff is linked at the bottom of the website, quacs.org, so feel free to go there and join our Discord or check out our GitHub, open an issue, make a PR, something like that.
All right, no questions, I guess.
I have one actually. So you are still doing conflict resolution using depth first search just on the client side, right?
Right. Yeah, so as we said, we couldn't really think of a more efficient algorithm than a depth first search. We don't think that one exists. So our efforts were focused on just optimizing that depth first search to run as fast as it could.
Okay. I worked on, I was actually a QuaCS developer a few years ago, and I was tasked with improving the conflict checking, rewriting it from Ruby to Rust, and finding a faster algorithm than what we were using at the time. And I never got any, working, copy of anything that got deployed to YACS, unfortunately. But I was using let me see what it's called. There's a Rust crate called Cassowary, which is a constraint resolution library. So definitely something worth checking out if you're looking.
I actually looked at your code once. because we've poked around the YaCS repo and looked at some of the stuff, and I remember there being something like that.
Yeah, again, it never really came to fruition, but yeah,
that's definitely something we can look at. I think someone else suggested using a constraint solver, and we didn't really approach it because at the time the site was running fast enough and we're not really familiar with it. But that's a good idea. We might check that out again.
I think we also looked at it, and there's some overhead to that, because it has to deal with lots of different things.
Oh yeah, I'm sure there is. It might not be the perfect solution, but it would just be cool to consider, in my opinion. Here, I'll drop a link to the one I was using in the workshop channel.
Cool, thanks.
You're welcome.
All right.
Hey, I have a question real quick.
Yeah, sure.
For anyone new to, or I guess unfamiliar with Rust, such as myself, what do you suggest? I guess either of you guys suggest for getting into the language, or I guess what resources did you use, since you seem pretty experienced at this point?
So for me, the biggest thing I did was reading through the Rust handbook or Rust book. I don't remember the exact name. It's a very helpful resource. At the start, there's a bit of if you don't know what programming is and how it works, it really starts at the beginning. But it's very helpful with teaching you the nuances of Rust. And then from that point, really, it's just practicing and writing Rust to get better at Rust. Yeah, Nia sent it in the workshop channel.
Gotcha. Thank you.
All right. Well, thank you for coming to our presentation. Who do we send the attendance list to?
You could just send that my way. I'll put it in for you guys.
All right.
We have a few screenshots from different points of the presentation, so.
Sure, no